Zero, but inside. Okay, with this. Okay, so inside this region, the vorticity is very high. Outside is, say, almost zero or small in comparison with what happens inside. And the solution are regular solution. But when you take the size of your region to go to zero, they become singular. They develop a delta. Okay, I could take, yeah. I can do this. Hello. It's okay? Okay. Okay. So yeah, this is more or less what I will discuss. This problem has a huge history, and I dare to devote just one slide to the two-dimensional case. Sorry for that. So if you are in dimension 2, it is well known that the region is a small region around points, and these points, in order to have a solution with that form, those points have to satisfy an Hamiltonian system, which is the one written here. So if you have a certain number of points, xij dot has to satisfy this Hamiltonian system, which is very old, and it has a name. At least this is the name I know. It's the Kirchhoff root dynamics for the points, or the vortex model. So the question is, assume you start with a vorticity concentrated around regions, small regions, at around certain point that I just called psi j of 0. Then what happens to the solution if you let it flow? And Marchioro and Pulvirenti, in several different contests, bounded domain, etc., they just started with a blob, and they proved that as long as you have a time interval in which there are no collision between points, then the solution, the vorticity, remains concentrated. And if you take the limit as epsilon goes to 0, you get that the limit in vorticity approach a sum of Dirac delta with a sum kj, that number kj. What we did, and this is somehow a way to introduce what I want to do later with Juan Manuel and Zhu Cheng, is to revisit, if you want, this type of result, and prove that there are solutions with concentrated vorticity. The shape of the solution we constructed can be described pretty well and with details in particular around the point of concentration, around the vortices. And in fact, they look like a scaling of the Kaufman-Scully stationary solution that was introduced by before by Thierry. And so our solution looked like that. We construct this solution with a method completely different that we call the inner and outer gluing procedure. And that I would like to present to you in a different context, the context of the leapfrogging. And this method, despite of the fact that we cannot start with any initial condition concentrated, but it gives us information, in particular, an information like that, that tells you that when you take epsilon to 0, the velocity approaches the sum of Dirac delta with a certain speed in epsilon. Information that, for instance, cannot be recovered by the construction, as far as I understand, of Malchior and Pulvirati. Okay, but what I would like to discuss is about this question in 3D. So the equation in terms of vorticity, now vorticity is a vector field, is this one, and the question or the situation or the topic is about a solution that have vorticity, these times concentrated along a curve, say a tube of size epsilon along a curve, and this curve is evolving in time. So you can think of a tornado. This is what I think. The velocity is very fast. You're around the line, the imaginary line of a tornado. So the vorticity is very high there. Outside is almost 0 and points in the direction of the tangent, more or less of the tangent to the curve. So this is what I wanted to express here. So yeah, this is my tornado. The green tube is our epsilon tubular neighborhood of the curve, which I parameterize by arc length S, and it evolves. So tangent, binormal, and normal, and curvature. So in 1904, the Rios, using the Biot-Savart law, formally derived the law of motion of a possible vortex filament. Okay. And in fact, he took the Biot-Savart law. The first term is something of order 1 over epsilon, which has only rotational direction. So he took the next order term, which comes with a logarithm of epsilon. Epsilon is always the size of our tiny region. So it's the size of the tube along the curve. And he discovered that the evolution of this curve goes by the binormal flow. So gamma t is 2 times the curvature along the binormal. There is this c, which is related to circulation, and there is this log epsilon. But if you don't want to carry this log epsilon with you, you can do a simple scale in time, which somehow suggests that if such an object exists, it exists for short time. But short of what kind? Short of the kind 1 over log epsilon. Okay, where epsilon is the 2. This formal derivation have been obtained several times. We also have our derivations. But yeah, what the big problem, the big question is about the following. If you have a curve that evolves by the binormal flow, is there a way to find the solution of the 3D Euler flow that approaches a Dirac mass along the curve in the direction of the tangent of the curve? This is, we call it a vortex filament conjecture. In the work of Helmholtz, also Dario, when he reported his discovery, I mean his computation, this question is suggested, but probably the first time the question was put in words was by Benedetto Cagliotti e Marchioro in 2015, and also in a paper by Gerard and Sayce, 2017, in which they prove the other way around. So what they prove is that if you know that the vorticity are very concentrated around tubes of these evolving curves, then the curve evolved by normal flow. Okay, so this is an open problem, except in very special cases. There are many interesting construction of curves evolving by normal flow. I just want to mention the work of Hashimoto, the group of Luis Vega and Valeria Banica, that they constructed very interesting example. But the very simple cases are these two. So and they have a lot of symmetries, and you use those symmetries to simplify the problem. So the first example is the helix. So if you take an helix and you evolve the helix in such a way that it rotates with constant velocity, then it solves the binormal flow. And of course, you have the circle that travels vertically, as this morning was described, with a velocity that, in order to satisfy the binormal flow, has to be 2 times divided by the radius, so 2 times the curvature. It goes up, say, in this picture, with that speed. So what about the constructing solution, real solution of the Euler equation with the characteristic I just mentioned before? And let me start with the helix. So here it is written an helix for any tau. You have an helix, and so the helix doesn't really change its form along the evolution. It's always, for any tau, an helix. And if you choose properly the velocity, A1, the rotational, and B1 when you push it up, in terms of the radius of the circular helix, and h, the vertical jump that you do, then for any tau, this kind of helices satisfy the binormal flow, the equation of binormal flow. And what we did was to construct the solution for Euler. Let me mention how we did it briefly. So we learned from a paper of Ettinger and TT that you can use brute a lot the symmetry of your situation. So if you consider a vorticity that satisfies a certain helical differential symmetry, and moreover you assume that the initial velocity is orthogonal to the symmetry lines. In other words, the initial vorticity is a tangent to the lines, to the helices. Then this property is preserved along the Euler equation. And this is very important because this property kills the vortex stretching term in the Euler equation and simplifies a lot the problem. And in fact, so if you then look for a solution, vorticity that are parallel to the tangent line of the helices, and so there are solutions of this form where omega here is a scalar function. It depends now only on two spatial variables and a time t. And so your difficult equation boils down to an equation in R2, which is like Euler in 2D, but the Biot-Savart law, the relation between the stream function and vorticity is different. But it is an elliptic operator. It's not the Laplacian. What I mean, it's a different operator that in any way you can treat. And there is a further simplification you can do. You can get rid of the time derivative if you put the following ansatz. So our now scalar function w, it's just a function w of two variables x and y, and you rotate it with a constant velocity that I called alpha. So you get rid of the wt, and your problem becomes very elliptic, which is nice. Well, depends, but so using the trick that was written here, you then call w, you choose a nonlinearity f, you say w is f of this expression here, so that the first equation automatically is satisfied, and you are now looking for a solution to this equation, which is an elliptic equation in R2. And this is what we solved. Now, another example, a beautiful example of binormal flow is a circle, a circle here of radius r that travels up, say, with a velocity alpha 2 divided by r. So, and the question is, okay, the solution of the Euler, whose vorticity are around this circle, are called vortex ring, and they exist. They are well known. So in this case, you also use the symmetry of the problem. So here, this picture doesn't depend on theta, and you consider the axisymmetric Euler that I am not going to explain because you are experts. So yeah, so velocity and vorticity, they are expressed along the tangent in the plane. I mean, the radial direction, the tangent direction, the zeta direction. And if you do this change of variables, so omega theta, all the components do not depend on theta. And if you call capital W omega theta divided by R, U1, U theta divided by R, and psi1, psi theta divided by R, psi is the stream function, you get to this equation here. Then this is a system of 3 equations, say. So this is the last equation describes you the the relation between the vorticity and the stream function. And we consider the even simpler case of no swirl. So U1 is 0, and the first equation is gone. And then you get to this equation here. It is written in this way, okay? So it's this log epsilon. It is there because you want to get rid of the log epsilon in front of the binormal flow. So you scale in time. And this problem is seen in an interval of time of order 1 in epsilon, from 0 to capital T. There is an R here, WT, then the gradient perp of R square psi, gradient W, etc. So I will call Laplacian 5 the relation between the stream function and the vorticity. And it's written up there that X is the point in the alpha plane of component R and zeta are positive. Okay. So, well, Helmholtz himself described a vortex ring. And what I would like to describe to you is the construction that Frankel did of this vortex ring. This is because Frankel solutions say, or in reality, an approximation of Frankel solution will be our building blocks to construct the leapfrogging. So what did Frankel do? He looked for traveling solution of the above equation, getting rid of time. And so you have again something like gradient perp of something dot gradient of W, where psi and W are related in this way, and you use the same trick as before. You put W equal F of what is inside the gradient perp. And you have here an elliptic equation. Now, what are you expecting here? So you have R, and you're expecting that the vorticity, but multiplied by R, is something like a Dirac delta at some point that, for simplicity, I take on this axis. Okay. So we expect that R times W epsilon, as epsilon goes to 0, approaches a Dirac delta. Now, if this is the situation, and given the relation between the vorticity and the stream function, you want to know, in order to talk about or to understand the stream function, you want to find the Green's function for this operator. And you can give a rather precise description of this Green function. You see, since locally around the point P naught, your operator up there is basically a 2 Laplacian. So you have this logarithm that comes from the Green's function in R2, but then of course you have a correction, and observe this correction is linear in R, but you don't have anything linear in zeta, okay? And this is because your operator is slightly different than the Laplacian. And then you have other terms, which, if you stay relatively close to your point P naught, P0, are like quadratic. Okay, so, but of course we cannot take as our stream function this G is singular. And we want something that is not singular. So we brutally and very, I don't know if Frankel did that, probably he was more sophisticated, but in the way I want to produce this this construction, you just add here epsilon square. So you see you have, and I just dropped the quadratic terms. So your vorticity at the first glance multiplied by R, but we are close to this point. So close to this point, R is just R0, is the Green's function with this, it's wrong. It's epsilon square plus x minus p naught square. There is a, okay. And then you choose the nonlinearity, and we choose the exponential nonlinearity because we know how to work with this equation, the Liouville equation in R2, and why this is related to what is written there. It's because this is just the Schooley, Kaufman-Schooley vortex. Okay. In fact, capital U is a bad name because U is for velocity, but here capital U is for vorticity. So sorry for this also. Okay. But this is the Schooley. Okay, so you take that, you take this approximation, and in fact, the Frankel vortex ring is something close to these two functions. Let me try to understand now the velocity alpha at which this vortex ring travels. I mean, alpha, we know that the ring travels with this velocity, but here we are fattening the ring. There is a tubular epsilon dependent thing around the ring. So I want to find the velocity for the vortex ring, not for the circle going up. So what you can do is zoom around P naught and compute the error. It's convenient to multiply it by epsilon to power 4. And then you get a first term. I think this is epsilon square anyway. You get the first error term, which is of size epsilon. It goes multiplied with the capital U, the Schooley vortex, so it decays fast. But it's in mode 1. You have a y1 here, and then there is something, and what is left outside is of order epsilon square. Okay, so in order to improve, it's not clear in these slides, but if you linearize this equation around the psi 0 naught and you scale property, the important linear operator that you get is this one, that I called L because it is the linearized equation for the Liouville equation around the gamma 0. Gamma 0 is nothing but the log of, okay. And then you want to solve to improve this error, but the problem is that this equation has many invariances, not only by rigid movements, but also there is a scaling invariant. And these are all the bounded elements in the kernel. Now, if you want to solve, you need some orthogonality condition of your right-hand side is 0 with respect to this function. And they are almost all satisfied at main order, let me say, because here you have y1. So with respect to zeta 2 here, it's fine. And with respect to zeta 0, this is a radial bounded function. So you need this orthogonality condition. And this orthogonality condition tells you that the velocity of the vortex ring of Frankel is like the velocity of the circle, modified by a term of size log epsilon multiplied by a function that depends on epsilon, which is that you can expand even. It's capital O of 1, and then the next order term is epsilon square. You jump from order 1 to epsilon square. Okay, so what I would like to do now is to describe what we have concerning the leapfrogging. So the leapfrogging was this is a citation from Helmholtz, was really described by him in 1858. So what is the situation here? I have a movie, but I'm not really sure that, let me go to this. So you have two vortex rings, one is red and one is green, and they are very close one to the other. So they feel the effect of the other, okay? Remember that the velocity is proportional to 1 divided by the radius. So for instance, in this situation, we have a bigger radius, smaller speed, but the ring, the red ring becomes smaller, so it gains velocity, and it overcomes the green one that in the meantime enlarged his radius, so he was going more slowly. Okay, so this is what Helmholtz described, and this is what I would like to discuss now. So no movies, because I'm not really sure. So we want, this is to solve this equation here. So it is still axisymmetric. It is still with no swirl. But the main point is that you cannot really get rid of the W sub t. It's a truly dynamic problem. And you still have this relation between psi and W. So what we did was, let's take two Frankel solutions. So these are our building blocks, and we add them up together. So the first one is 1 over Rj, epsilon j square, our capital U, centered at the first point, and etc. And for the stream function, we do the same. Okay, we just take. Now we assume that the points move. Now the points are not like in Frankel situation where, I mean, then you have to rotate and then you go up in zeta with constant velocity. This is in Frankel situation. Now our points P1 and P2 have to depend on time. Now, since, so in particular, this Rj, which is the first component of Pj, is a function of time. And in order to have that the circulation along the curve is constant in time, we have to ask that also the scaling epsilon j are a function of time. Okay, but we will be, I mean, these points will be relatively close to P naught. Okay. So you ask that Rjt epsilon j square t is constant in time, and we say that this is R0 times epsilon square. So if you think of epsilon j that you will encounter here, you can think of epsilon j as epsilon, And what is next is, I think it is this. It's a function in time of this size. Okay. So it's basically, I did it wrong, sorry. Okay, 1 plus what is left is 1 over square root of log. Okay, and what is this R0? Well, this R0 is, so in the equation we have the alpha, which represent again the velocity in the vertical direction. And we take R0 like this, okay? So I would like to describe this, the error, if you take these ansatz around the point P1, which is okay. I mean, so we need to scale. Y is the scale variable and rho is related to y in this way. And I will use this notation. So for a function, I will call a function AK, a function that has mode k if you Fourier expand it in theta. Okay. And this EK1 and EK2 are, say, capital of 1 as epsilon goes to 0. So if you compute the error, namely, this is the operator you want to compute, you multiply now by epsilon 1 to power 4. So this is the equation you want to satisfy. You get that the first error is of order epsilon 1 multiplied by this expression here that involves the points times the gradient of the Scully vortex. And what is next is something of order epsilon square log epsilon times a function of mode 2. So the first one is mode 1. And we take the points to have this parenthesis equal to 0. So let us see this parenthesis equal to 0. How does it look like? It looks like that equation over there. If you just take the case of 1 point, so Frankel's single ring traveling, you don't have this interaction there. And what you get at main order is this. I didn't take the capital of 1 over log epsilon, this correction here for the ring. This is for Frankel. This is for 1 ring. So you get as expected that I don't know why it is not working. Okay, so so you solve. Then we take this a modification of these points, this Pj, that are like the points of Frankel plus a Qj. And if you put it inside upstairs in the equation, you realize that you can see it. It's like dtq equals 1 over log, and what is there is 1 over q. So it's like q square equal 1 over log. So the rate scale here is 1 over square root of log. So if you take this point here like that, the bj, the bi, satisfy this system, okay, which is known in the literature, and it's called as the leapfrog system. Okay. So assume we choose the points in this way, we kill the epsilon size term, and we get to epsilon square log epsilon. So this is the theorem. Assume you have in an interval of time 0 capital T a solution of BI of the leapfrogging equation, then we can construct a solution that looks like the Scully vortex, the sum of two Scully vortex in this way, and the stream function is like the stream function of the leapfrogging, but two stream function added together. So the situation is like this: you have P0, and then the point P1 and P2 are close to P0, and relative distance here is of size 1 over square root of log epsilon. Okay. So this is the picture of the leapfrogging. Now it is traveling up. You have over there the distance of the 2 points, P1 and P2. And the epsilon is the size of the tubular neighborhood around the P1 and P2, where the vorticity counts. Okay, so this is more or less the picture that you have. I would like to go into the proof of these results, more or less, which also gives me the opportunity to explain our strategy, which is sort of in part related with the construction we did in 2D. Okay, and the basic ingredient, which of course is of this construction, is a first approximation, good one, and then to find a close by solution using the inner and outer gluing scheme. I would like to present you first the inner and outer gluing scheme to tell you how well should be the how good should be the approximation, and then I will describe to you the way we construct the approximation. So S is the operator we want to study. So we want to find S equal to 0. And let me consider a cutoff function. So this is the picture we had before. Epsilon is the size of the tube. 1 over square root of log epsilon is the distance of the 2 points. And I take a tubular neighborhood of size 1 over log epsilon around P1, and then I turn. Why this? So I have this situation here. So this is epsilon, then the point 1 over log epsilon, and the other point is here at a distance 1 over square root of log epsilon. Okay. Now, okay, so let me say we start with an approximation, which is called the star, psi star, W star. Then we look for a solution, a real solution, where the remainder is written in that form over there. So it has to be described just, I don't know, the vorticity. The vorticity has a first part, which goes with the cutoff, and it has the same form of the principal part of the vorticity, namely 1 over Rj epsilon j squared times a function of the variable x minus pj over epsilon j. So what we are doing here, then we take this neighborhood and we zoom it in the y variable. This is here. And there is another part, which is called phi out, okay? And it is expressed in the x original variable. Okay, you take all this, you plug it inside the equation, and you can write the problem as follows, or better. You decompose somehow. You have the following observation. You recognize two inner problems for each point and one outer problem. And if you are able to solve them equal to 0, they give you a solution. Now, of course, these problems are coupled. The inner, which are this phi j, here it enters the psi outer, and also the other way around. Okay, so one point is to choose the topologies in such a way that these are at main order decoupled. So let me start with the EJ inner, sorry. And let me show to you, it's a little bit boring, but it's nice, the power of choosing, of choosing Rj epsilon j square independent of time, so the circulation is constant in time. One part, of course, of the operator is the time-dependent part, right? So if you assume that your phi tilde, we are looking inside, so your phi tilde as that form, you do the computation, and you realize that there are several things that simplifies in such a way that you are left with what? With this term here, epsilon square log dt, fine. You have a term here, this the dtp will be of size epsilon square, so here we are at size epsilon cube, but times something which is the gradient of phi. If you start with a capital U, this is in mode 1. But the most important part is this B0, which is of the same size as before, epsilon square log epsilon. But if you put a phi, a radial function, this B0 produce you only mode 2 function with epsilon square and mode 1 function with 1 extra epsilon. And this is one very important thing that we will use. This is a simplified version of the inner equation. So you recognize the red part, which is the time derivative. Then you recognize a linear term, the second line in blue. We are linearizing around our Frankel solution. This is very simplified. But you recognize, for instance, the presence of the geometry, 1 over Rj, y1, gamma 0 is the geometry, is the curvature that is coming. Then you have a quadratic term where I left also our psi out enter, and then you take the final error, so your approximation, you compute the equation on your approximation, you call it final error, and you take just the part of the final error in where the cutoff eta j is important, okay? And this is more or less how it looks, the simplified version of the outer problem, okay? Let me just mention something that if you want that the inner phi j do not destroy the outer problem, you have to look how the phi j enter in the outer problem. It always enter multiplied by a derivative of the cutoffs, so that in order to have it decoupled, A way to do it is to ensure that the Fj decays so that far away is small. And far away is where, multiplied by the derivative of the cutoff, you see it in the outer problem. Oh, okay, so once we write this decouple, whatever, problem inner and outer, a key point for our construction is to solve that linear operator up there, which is the important linear operator in the inner equation, okay? And what we proved, I don't have time to prove it, but is this a priori bounds. And these a priori bounds tell you exactly all you want to know. First of all, you lose epsilon square, which means that you have to start with an initial answers good enough. But also, it gives you that your error has to decay. This u to power minus 1/2 is rho square. So you need a decay. It's enough for us to have decay 1 over rho cubed, because we are in a domain, it's in a radius of size 1 over epsilon. We lose a log epsilon, but this problem is sort of the log epsilon. You just decide not to count the log epsilon. It's not there where the game is done. So what is this? So yeah, this is what I wanted to do. We want to arrive to a final error of this form, epsilon to power 5, because otherwise we lose. So we lose epsilon squared, then we put it back, we have a quadratic term. You need epsilon square, epsilon to power 4, and you decay rate of rho cubed. And the log is, I will not keep trace of the logs. So how do we improve? So this is the initial approximation. Our points will be this here with the BJ plus something that we have to adjust, but it will be much smaller. It will be size epsilon square. Okay, so this is the inner equation again. You have a term like epsilon square dt. Then you have a linearized elliptic operator and a quadratic term. Okay, and you start with an initial error, which is epsilon square log epsilon mode 2. So you use, this is the elliptic part to get rid of this initial error. This operator can be written in this form here, is d theta of the Liouville operator that I mentioned to you before. It's an operator highly degenerate. All the radial function lives here besides all the elements of the kernel of the Liouville operator. So, but we are lucky. Our initial error has mode 2, so you can invert. You can invert and you get a new error. You lose 1 rho in decay, but you gain 1 epsilon. And the new error is in mode 1. Then you use again the Liouville operator, adjusting the points. And you gain 1 epsilon, epsilon 4, and you lose 1 rho. But you're stuck now because you get an error of mode 0 and you cannot use the Liouville operator. You cannot. So you use the ODE, which is bad. The ODE makes you lose 2 epsilon. And so the error you get is E3 compared with E2, you have 1 epsilon more, less, sorry, less. But it's an error of mode 1 sine theta. you don't have cos theta. And this is the key argument for our construction that I will describe to you in these slides because, okay. Unfortunately, there is no pointer. So we start with E0, E2. We use the Liouville operator. We get to a mode 1. We adjust the point and we use the Liouville operator and we get to a mode 0. The mode 0, we solve the ODE, we lose epsilon, but we get to a sine theta. What is the compare E3 with E1? They are both epsilon cube, rho cube, but you don't have cosine in E3. So you're lucky because you use Liouville and you don't produce mode 0. You go to mode 2. Mode 2, Liouville, you get to epsilon 5, mode 0, epsilon 5 is good. Unfortunately, you don't have enough decay. We use the transport equation to gain the decay. We lose to epsilon, but now we know how to gain epsilon. And we start here with E6, which compared to E1 is epsilon square, but with 2 more rho. So we can. And let me just conclude. Sorry, I'm late. With this comment. So the system for the point little bj was derived by Klein, Maida, and Daran in 1995. Gerard and Smets constructed the leapfrogging for Gross-Pitayevsky. And finally, well, of course, we would like to say something about the general vortex filament conjecture. But there is a beautiful work by Gallet and Smets on the spectral analysis for the straight vortex filament that may be combined with our thing. Maybe one day we can say something about the general problem. Okay, thank you very much. For the mic, it's here.
Thank you. I have to dredge my memory back 50 years, but I think a student of Edward Frenkel, John Norbury, did further work with Frenkel. And if my memory is correct, it was about the existence as you go more to fat rings than thin rings. Is that right? And I think you're talking about thin rings, aren't you? So how, if you forgive the way I'm putting it, how fat can you get? How fat can you go in terms of the rings?
So we need the ring to be small. Our ring is small. And yes, sorry, not small. The radius is, so we have 2 rings. The radius is fixed. But the thickness of the ring, yes, of the 2 rings are both small. Yeah.
Is there any hint in,
for sure, I am sure that there are. So, but as far as I know, this rigorous construction of the leapfrogging was for this equation for Euler was not known. So for Gross-Pitayevsky, yes, but not for Euler.